here what we have is an example of a massive pulley with two masses hanging over it that are connected by a string or a rope. So we're going to be going ahead and solving this problem, making sure that we take into consideration that, again, this is a massive pulley, so a pulley that has mass, which therefore has a moment of inertia and has rotational acceleration. And when we think about that, that ends up giving us two tensions in the string that are not equal. So the first thing that we're going to do is we're going to draw a picture of this scenario. So we have a disc-shaped pulley with a moment of inertia given by 1/2 mr squared. It has a mass of 5 kilograms and a radius of 0.2 meters. I'm just going to go ahead and label my masses. Then we have mass 1 has a mass of 4 kilograms. Doesn't really matter what side you put this on, so I'm just going to go ahead and I'm going to put mass 1 right here. And then we have mass 2, which has a mass of 8 kilograms. So what we want to find out is we want to find out what is the acceleration of the system, and then we want to know what is the tension of each string. The first thing that we want to do is we want to identify our positive direction. Since the 8 kilogram or the mass 1, let me go ahead and label this, or mass 2 is 8 kilograms, we're going to assume that the rotation goes in that way. So this would be a clockwise would be positive, down would be positive on this mass, and then up would be positive on that mass. So making sure that we keep that system of which way is positive and negative into consideration. Now what we're going to do is we're going to draw free body diagrams for each of our masses and create Newton's second law equations for that. If I pay attention to mass 1, I know that up is positive, which means that the tension in the string is going to be larger than the force due to gravity on that mass. If I think about the sum and write my Newton's second law of all the forces in the y direction, I'm going to have T1 minus Fg1, and that's going to equal M1A. Be very careful about clearly labeling your masses and things like that in these problems, because we are going to be combining three equations and you don't want to get those masses mixed up. I'm going to rearrange this. Actually, let me erase that. I'm going to break apart my Fg, so is this going to be T1 minus M1G, and this is going to equal M1A. So this is my first equation. I'm going to do the exact same thing with mass 2. Now downwards is going to be positive, so this is going to be Fg2, and this is going to be bigger than my T2. And again, T1 and T2, because the pulley has angular acceleration, those are not equal. The sum of all the forces in the y direction is going to be equal to Fg2 minus T2, and this is going to equal to M2A. Breaking apart my Fg2, that's going to be M2G minus T2, and that's going to equal M2A. So these are my first two equations that I'm going to be looking at. And I want to write my last equation, which is going to be that of the pulley. Now I have two torques that are acting on the pulley. I have torque 1, which is going to be corresponding to mass 1, and torque 2, which is going to be corresponding to mass 2. And we are going to say that, again, this is the positive direction. The sum of all the torques in this direction are going to be equal to torque 2 minus torque 1, and that's going to be equal to I alpha. So notice that I am plugging in the rotational versions of those equations. So instead of forces, I have torques, and then instead of m times alpha or m times acceleration, I have my moment of inertia times my acceleration. Now what we're going to do is we're going to break apart my torques, and we're going to say that this is due to tension 2 over a radius, and this is going to be due to tension 1 times a radius. We're going to plug in our equation that we were given for the moment of inertia, And we are also going to plug in the angular relationship to I alpha. So we know that, not I alpha, but alpha, we know that the linear acceleration is equal to r times alpha. So I want to get that into my linear form, because what we're going to see is that my linear acceleration, is the one thing that's going to connect all three portions of this problem. Now looking at this, we can cancel out one of these r's, and since we have an r in each of these expressions, that will cancel out with that r as well. So we are able to cancel out a bunch of stuff, and we end up getting T2 minus T1 is going to equal to 1/2 ma. So now this is where we're going to start cleaning some stuff up. We are going to start combining some equations. So if we look at what we have right now, T1 is an unknown, A is an unknown, T2 is an unknown, and this A is an unknown. But again, these two A's that I just underlined are going to be the same. And again, here we have an unknown, which is related to my equation in pink. And then we have T1, which is also an unknown, which is equal to my equation in blue. And then my one variable, which is again acceleration, which we see in all of these problems. So what we want to do is we're going to combine our equations and try to get rid of our tensions so that we only have one unknown. So we're going to start combining our equations. There's lots of different ways that you can rearrange these. I am going to rearrange what I have here in white and say this is T2 is going to be equal to 1/2 ma plus T1. And I just realized that I should be more specific with my m here, since we're going to start combining these equations, and I'm going to call this MP for the mass of the pulley. Now I just rearranged this equation to solve for M2, so I'm going to take this and I'm going to plug it into that position right there, and I end up getting M2G minus 1/2 MPA minus T1, making sure that we subtract that T1 since there is a negative in front of my T2 here that needs to get distributed throughout this entire expression. And this is going to be equal to M2A. So right now what I have is I combined these two equations and I got rid of T2 as an unknown variable. I still have T1 as an unknown, and again my A's as an unknown, but that's what we're going to end up solving for. So what I can do is I could take this equation and I could kind of just add these together. You could either rearrange my equation in blue and solve for T1 and then plug it in here. Or if I realize that this is T1 minus M1G is going to equal M1A. If I were to add these two together, we see that these cancel out. And so what I would get is M2G minus 1/2 MPA. And then we'll have minus M1G, and this is going to be equal to M2A plus M1A. Now I'm just going to move over my other variable that has A over here, and I'm going to go ahead and then factor out all my A's in those equations. So it's going to be M2G minus M1G, and this is going to be equal to M2A plus M1A plus 1/2 MPA. And almost done. We can factor out G. So I can pull G out of here. And I could also pull A out of here. And if I divide both sides, what I end up getting is that A is equal to G M2 minus M1, all divided by M2 plus M1 plus 1/2 MP. If I go back and I plug in all of my variables that I have, so G is equal to 10 meters per second squared. The mass of mass 2 was 8 kilograms minus 4 kilograms. And then we're going to divide that by 8 kilograms plus 4 kilograms plus this is going to be 1/2, and the mass of my pulley was 5 kilograms. We end up getting my acceleration when I plug this in to be 2.76, and this is going to be meters per second squared. So this is my acceleration of the system. Now, that solves for the first portion of that problem. So now what we're going to do is we're going to take this variable. Let's go ahead and grab this. We're going to make a copy. And we are going to use that and my tension equations to solve for the tension in my two strings. So again, here is my acceleration. And if I look back and I look at my equation for, let's say, mass 1, we were told, or we found out that the sum, or that the T1, let's actually get rid of that. We solved that T1 minus M1G is going to equal M2A. So we can solve for T1. I could pull out M1, and I just realized I accidentally wrote M2. Let's get rid of that. M1A. This is going to be G plus A. That's going to be equal. We can plug this in, and we will get T1 to be 51.06 newtons. And again, we should see that the tensions in the two strings are not equal. So let's go ahead and look at mass 2, which has tension 2. If I were to write that down, we had M2G minus T2 is going to equal M2A. And if I rearrange this equation for T2, I get T2 is equal to M2G minus A. Plug in all my variables, and I get the tension of the string to be 57.92 newtons. So I have all these variables. This problem could have also asked you to solve for the rotational acceleration of the pulley. And if you were to do that, the only thing you would need to know is the radius of the pulley, which we were actually given in the problem. We were told that the radius of the pulley was 0.2 meters. So we could have converted that into our angular acceleration by dividing by r, and we would get our angular acceleration. The problem did not ask for that, but it is important to know that that is something we could be solving for. So that is all for this problem of solving for a massive pulley that has two masses.